we're going to be doing another motion problem. In this case, we're going to be looking at particle motion. Let's go ahead and read this problem together. It says the acceleration, right off the bat, that's a key word here. This equation that we are given is the acceleration of the particle, not the position. So if this is the acceleration, how do we get to position? How do we get to velocity? Well, remember with our map, we need to take the integral to find velocity. Integral of acceleration is velocity. Integral of velocity is position. And this is after t seconds. So for example, after 1 second, if you plug in 1 for t, you get 2 for the acceleration. After 2 seconds, you get 8, so on and so forth. Acceleration is basically the rate in which the velocity is changing. You can see that when you see a car speeding up or slowing down. The particle starts 8 nanometers to the right of the origin meaning 0, 0, and begins moving to the left at a rate of 4 nanometers per second. So let's underline a few more things. It starts 8 nanometers to the right of the origin, so that would be its initial position, and it begins moving to the left at a rate of 4 nanometers per second. Okay, so we want to draw an arrow here and mention that when the units are nanometers per second or meters per second, that's referring to the velocity, okay, v of t. So we'll be more specific in a second, but for right now, we're given its initial velocity, we're given its initial position, and we're given an acceleration equation, right? So all that being said, the question is going to ask for when does the particle start to slow down. Let me see if I can zoom out here a little bit. So, we really want to underline the slow down part because that's what we're trying to ask for. And we want to figure out when does it slow down. So t is equal to what? At what point in time does t equal when the particle starts to slow down? So before we get to this question, I actually want to show you what this would look like as a simulation so you can see this particle moving. Okay, so I've got the particle pulled up here on the the t-axis rather, right? And you can see that it's 8 nanometers from the origin, 0, 0, and it's just going to be moving right and left, right and left. I've plugged in the requirements as far as the acceleration goes. Again, the acceleration equation is right here, and we're just going to watch it move so you can get an idea of what the movement looks like. Then we'll come back later on and verify our results. So let's go ahead and click OK. Watch this. So again, it starts moving to the left, right? And it has its own movement going on. You can see it goes all the way to the origin, then it starts moving back to the right. Okay, then it goes way to the right to 24, and it looks like it stops there. So, okay, so we can run this simulation multiple times. And again, the question 1 is asking, when does this particle start to slow down? So you might be able to see that by watching it. But certainly we need to do the math to figure out at what point at time t for this t-axis did it start to slow down. Let's go ahead and do the problem. First of all, we want to write out what is given algebraically. Remember, that's step 1. Anytime you're doing a motion problem, write out what you're given algebraically. So in this case, we were given a of t equals 6t minus 4. That's what we were given. Step 2, convert what is given verbally to algebraic expressions. So notice in the sentence it says the particle starts 8 nanometers to the right of the origin. Again, if we look at our simulation, we can see that. Okay, so what does that mean? That's its position. And remember, position is denoted by s of t. In this case, it's going to be s of 0 because it's an initial position, so starts. So at t equals 0, position is 8, therefore s of 0 equals 8. Another part of the question says it began moving to the left at a rate of 4 nanometers per second. Okay, now with particle motion, if it's moving to the left, it's going to be negative. If it's moving to the right, it's going to be positive. And since it's moving to the left, we have v of 0 equals negative 4. If we want to, we can put the units there. That'd be nanometers per second. And remember, a nanometer is a very small thing. So again, if we go back to our simulation, this is moving at negative 4. When it first starts out, it's moving negative 4 nanometers a second. Now, of course, you can see it slows down at some point, and then it speeds up. We will figure out all these types of things as we answer more and more questions about the particle. Step 3, we want to convert the verbally stated question into an algebraic expression. So in the question it said, when does it start to slow down? So we want to figure out some t value. Next, this one's a little bit trickier. Start to slow down. What does that mean? That means the speed is decreasing, right? At what point does the speed begin to decrease? If it's increasing, it's accelerating, right? If it's decreasing, it's decelerating. So the answer is when the derivative of speed becomes negative. Okay, why? Because, and I want to be very clear about this, there's a slight difference between the derivative of speed and the derivative of velocity. Okay, the derivative of velocity is acceleration. The derivative of speed is still acceleration, but it's a vector of acceleration, meaning it could have a different sign. Okay, so we want to be very clear about that. Whenever something starts to slow down is when its speed decreases. So for me, the easiest way to figure this out is to find the speed equation and then take the derivative and see whenever that's equal to 0. So d dt of the absolute value of velocity is less than 0 for the first time. That will tell us when it starts to slow down. And remember, the absolute value of velocity is speed, so that's why it's like that. Okay, let's move on to the next step, is map out the relationship between position, velocity, and acceleration. So again, remember, the position is s of t, the derivative of s of t is velocity, and the double derivative, or second derivative, is acceleration, which happens to be the first derivative of velocity. If we're going even more detailed, the absolute value of velocity is speed, or the absolute value of the derivative position. If you integrate speed, you get total distance traveled, okay? But we're going this way because we're talking about slowing down. So we want to take the derivative, okay? So we have the prime up here, or ddt of the absolute value v of t will give us the instantaneous rate of change of speed, which again, I don't like to call acceleration, even though it's basically a type of acceleration. Just know that this is going to be different than if you just take the derivative of velocity, okay? Because it has the absolute value bars, so it's different. So it's instantaneous rate of change of speed. Solve the problem using either initial value or derivative procedures. So in this case, we're doing a little bit of both. We need to figure out the velocity equation first before we can figure out speed, so we're going to take the antiderivative of acceleration. Now, if you look at the original question, it says that the original acceleration is 6t minus 4, right? So we need to take the antiderivative of that and then plug in our value for, we'll figure out what c is. So the antiderivative of 6t squared minus 4, do the, 6t minus 4, do the reverse power rule, so add 1 to the exponent, so it's 2 divided by 2, and then the antiderivative of 4 is t, and then we will simplify that to get 3t squared minus 4t plus c. Now you're probably wondering, how do you figure out c? Well, they gave us an initial velocity. The initial velocity was -4. Again, that means that the particle begins moving at a rate of -4 nanometers per second. So we can let's draw some arrows here. We can replace v naught with -4. We can plug in 0 for t since it's the initial velocity, and then we will solve for c, and we get c equals -4. So once we replace c with -4, we get the velocity equation, which is v of t equals 3t squared minus 4t minus 4. So you can plug in any value for t at any given point in time, and it will tell you the velocity of that particle. For example, if you plugged in 1, your velocity would be 3 minus 4 minus 4, which would be -5. So it'd actually be going slower than when it started, because it started at -4. Pretty interesting stuff. So we do know it's slowing down at some point, right? Because it's slower than when it started. Now the absolute value of velocity is speed, so we're just going to take the absolute value of that formula that we just found. Now to take the derivative, we just take the derivative of this, which is the speed equation. And remember, wherever the derivative of speed is negative is when it's slowing down. When you take the derivative of an absolute value equation, you just basically put the whatever's inside the absolute value bars on top, divide by the whole thing on the bottom, including the absolute value bars, and then you multiply by the derivative. That's the chain rule. I do want to point out that you can actually flip this, and you can put the absolute values bars on top and the other on the bottom. Again, all this is actually giving you is a vector, basically, a negative or a positive sign. So it's just going to alter this. It's either going to make it positive or negative depending on the t-value, which is why I continually say that the instantaneous rate of change of speed is not exactly the same thing as acceleration, because acceleration, strictly speaking, is the derivative of velocity. So I like to differentiate between the two, and you could even be more clear and just always say the instantaneous rate of change of velocity versus instantaneous rate of change of speed. Okay, so we will simplify this. Just pull the 6t minus 4 up to the top there. And we want to find critical values so we can figure out where it's increasing, decreasing. Now you can factor this. So I'm going to go ahead and use a color for that. So the factored form of that is 3t plus 2, t minus 2. You can use the x method on that. Not going to spend a lot of time on that. Find 3t values. So set each of these factors equal to 0. You get negative 2/3. You get t equals 2 and t equals 2/3. This one will not count because we're starting with an initial time of 0 and increasing, so negative numbers do not count. So we've only got these two critical values. This is the only time, right, where this function could change sign, right? So it must be slowing down at one of these two t values, right? Let's go ahead and take a look and see what we get. So between 0 and 2/3, we plug in 0.5 and we get a positive number back. So we know that our speed, instantaneous rate of change of speed is positive there. So it's not slowing down there, right? Next, we're going to plug in 2/3 and 2, a number between those. Let's just pick 1. Now, why 2/3 and 2? Because those are our two critical values. So we'll plug in 1. And when we plug in 1, we get negative 2. Right? So that means it's negative on the interval. I do want to back up a second, actually. I guess it could have been slowing down initially, so I misspoke there. But because this is our interval here, because negative 2/3 was a intercept, basically, this number we plug in includes that, right? So had we gotten negative there, then actually it would have been slowing down when it started. But anyway, we got positive. So we got negative for 1 when we plugged in these two. Then you want to plug in a number after 2 just to see what's happening. So at 3, it's positive, so that means it's speeding up because the derivative of speed is positive. So what does this negative tell us? Well, it begins to become negative at t equals 2/3. So in between these two values, it's negative, so it's slowing down there. So let's answer this. The particle starts to slow down after time t equals 2/3. Now we want to give a really good reason for that, and then we'll be done. Because the derivative of speed first becomes negative after this time. And that's just the perfect way to explain this. You need to mention the derivative of speed. You need to mention that it first becomes negative at this time of t equals 2/3. That's it for this first question on particle motion and it slowing down. If you have any other questions about this, actually, before I finish, let's go ahead and look. We can actually kind of see, it's going to be hard to see, but at 2/3 is actually when the particle starts to slow down. And you can see it gets slow right there before 0, before it speeds up. All right, so that's it. Next question will be different, and we'll answer some different questions about this particle depending on the individual examples. Again, if you have any other questions about this, let me know.